I want to start today with a bit of a reality check. There is this pervading myth in the tech world, and I see it in marketing brochures, I hear it in sales pitches, that moving to the cloud is basically outsourcing your security headache.
Oh, absolutely.
You know the vibe. Just put it on Google Cloud Platform. They have 1,000 security engineers. They have guards with machine guns at the data centers. You're good. But looking at the stack of research you've brought in today, that feels like a really dangerous half-truth.
It's worse than a half-truth, honestly. It's the kind of assumption that gets CIOs fired.
Yeah.
Look, to be fair to Google, the secure by default claim is true for their part of the bargain.
Right.
The physical infrastructure, the fiber optics, the custom Titan chips in the servers, the perimeter fences around the data centers, that is world-class. You or I could never build that, but that is just the foundation.
They pour the concrete, but we are the ones building the house on top of it.
Exactly. And if you build a house made of straw on that world-class concrete foundation, the wolf is still going to blow it down. This is the core tension we need to unpack today. Google Cloud is secure by default regarding infrastructure, but your implementation, how you configure the thousands of knobs and dials in the console, is absolutely not secure by design unless you make it so.
And that leads us to this concept of the shared responsibility model. I know, it sounds like boring compliance jargon, but based on the SOCFortress series and the CIS benchmarks we are covering today, this is where everyone screws up.
It is the root cause of failure. The statistic that usually floats around the industry, and Gartner backs this up, is that through 2025, 99% of cloud security failures will be the customer's fault.
99%.
Think about that. 99%.
So when we read about a massive data leak, it's almost never some sophisticated spy cracking Google's encryption code. It's some guy named Dave leaving a bucket open.
Poor Dave. But yes, essentially, it's misconfiguration, it's a firewall rule left open, it's a permission granted way too broadly. Today, we are doing a deep dive into the SOCFortress series, which aligns with the CIS Google Cloud Platform benchmark.
The gold standard?
All right, the gold standard for hardening.
Oh.
We are going to move past the defaults and talk about how to actually lock the place down.
Okay, let's get into the weeds. If the default settings prioritize speed and ease of use over security, which seems to be the theme here, where's the biggest hole, is it the network?
You'd think so, but no. In the modern cloud, the primary perimeter isn't the firewall anymore. It is identity.
Identity, meaning literally who is logging in.
Correct. If I can log in as you, the best firewall in the world doesn't matter at all. I'm already inside. The CIS benchmarks put identity and access management, IAM, right at the very top. And the first, most common sin we see is the mixing of personal and corporate identities.
You mean using a generic gmail.com account to manage a corporate project?
It happens constantly. You're a startup, you're moving fast, you hire a freelancer, you just add freelancer.steve@gmail.com to the IAM permissions.
And it just works.
It works. He can code. Everyone is happy.
Until Steve gets fired.
Exactly.
Yeah.
Or until Steve gets hacked. See, you have no lifecycle management over Steve's personal Gmail. You cannot force him to change his password. You cannot enforce multi-factor authentication on his personal account.
Right.
If he leaves the project but you forget to manually remove him, he just has access forever.
That seems like such an unforced error. So the rule is corporate identities only.
Strictly. You enforce Google Workspace or Cloud Identity. That way, if an employee leaves, HR disables their corporate email, and boom, access is revoked across the entire cloud environment instantly.
Okay, but let's play devil's advocate for a second. Even with corporate accounts, people get phished, credentials get stolen. I assume you are mandated to use MFA, but the research suggests that standard MFA might not be enough for the heavy hitters.
This is where the landscape has really shifted. For a long time, getting an SMS code to your phone was the standard. But attackers have completely figured that out.
With SIM swapping.
Yes, SIM swapping, where they trick your carrier into transferring your phone number to their SIM card. Or they use MFA fatigue, where they spam your phone with approved login notifications at 3 in the morning until you groggily hit yes, just to make it stop.
I've heard of that. So for the admins, the project owners, the people who hold the keys to the kingdom, what is the actual defense?
Hardware. The guidance is explicit here. For high-privilege roles, you need FIDO2 security keys. These are physical USB sticks, like YubiKeys. You have to physically touch the device to authenticate.
So even if a hacker in another country has my password and has cloned my SIM card...
It doesn't matter. Unless they physically stole the USB key from your keychain, they cannot get in. It stops remote phishing attacks cold.
That is a significant upgrade. Now, moving beyond humans, the notes mention something called service accounts and refer to them as the silent killer. That sounds fairly dramatic. Why are we so scared of these?
A service account is basically an identity for a robot. It's what your application uses to talk to a database or what a script uses to run backups. The problem is how we traditionally authenticate them. The easy way is to generate a service account key.
Which is just a file, right? A JSON file.
It's a text file. And inside that text file is a private key that effectively acts as a password that never, ever expires. And because developers are human and they want to be helpful, they often check this file into GitHub.
Oh, no.
Or they Slack it to a colleague. Or they leave it on a shared drive.
And once it's out there...
Once it's out there, anyone who finds it literally is that service account.
Yeah.
And remember, robots don't use MFA. There is no phone to ping. If I have that key, I can use it from a laptop in a coffee shop in Siberia, and Google Cloud will just let me in.
So if these keys are so dangerous, why does Google even let us create them? What is the alternative?
The alternative is workload identity. It's a bit more complex to set up, but much safer. Instead of a static key file, you tell Google, hey, trust this Kubernetes cluster. When the application runs, it trades its verifiable identity for a short-lived access token.
Like a visitor badge that expires in an hour.
Exactly. There is no file to steal. If a hacker manages to grab the token somehow, it's useless a short time later.
And for the listeners who might have legacy projects running right now, how do they know if they have these ticking time bombs lying around?
You have to audit. There is a specific GradCloud command to list all user-managed keys. If you see a key that was created in 2019 and hasn't been rotated since, honestly, you should panic a little bit. That key is a massive liability.
Okay, so we have locked down the humans with hardware keys, and we are cleaning up the robot keys. But let's assume the worst. Let's assume someone does get in. This brings us to visibility.
Right. The absolute mantra here is, if it's not logged, it effectively did not happen. You can't investigate a crime scene if you didn't have the cameras rolling.
And Google logs things by default, doesn't it?
Some things. Admin activity is usually on. So, if someone created a firewall rule or deleted a server. But data access logs, tracking, who read a file, who queried a database, those are often off by default because they generate massive, massive amounts of data.
And massive amounts of data means a much bigger bill.
Exactly. But you have to weigh that cost against the cost of a breach. If someone is exfiltrating your customer database row by row, admin activity won't show it at all. Only data access logs will.
And where do we keep these logs? I felt like the research made a really big deal about centralization. Why can't I just leave them in the project where they were generated?
Think about the attacker's mindset for a second. If I compromise a project and become the owner, what is the very first thing I'm going to do before I start stealing data?
You are going to wipe the tapes.
I am going to delete the logs to cover my tracks. If the logs are stored inside the compromised project, they are gone. You need to create a log sync. You funnel all logs from all projects into a separate lockdown security project, maybe into a specialized storage bucket with a bucket lock on it.
So even if the production environment completely burns to the ground, the black box flight recorder is safe in a different bunker.
Precisely. And you need to keep those logs for a while. The CIS benchmark recommends at least 90 days, but really, for forensics, you want a year. Attackers are patient.
They just wait.
Yeah, they might compromise a low-level account and just sit there lurking, watching your network traffic for months before they strike.
That lurking concept is terrifying.
Yeah.
It really highlights why real-time alerts aren't enough. You need historical data to go back and trace their exact steps. Let's talk about the plumbing now, networking.
The network. This is where the concept of secure by default really falls apart completely.
I noticed the outline mentions the default network. When I create a new project, Google literally gives me a network named default. It works right out of the box. You're saying delete it.
Delete it immediately.
Yeah.
Before you deploy a single resource.
Why? Is it actually broken?
It's not broken. It's promiscuous. It's designed for ease of use, so you can get started fast. It has subnets automatically created in every single region of the world. It comes with pre-populated firewall rules that are very permissive. It implies a level of trust that simply shouldn't exist in a hardened environment.
So it's the party house of networks.
That is the perfect way to put it. You want to build a custom VPC. You want to explicitly define, I only need a subnet in Virginia, or I only want these specific ports open.
Speaking of ports, let's talk about port hygiene. I keep seeing 0.0.0.0/0 in the documentation. That is the code for the whole internet, right?
It is. And we see this all the time with port 22 for SSH and port 3389 for RDP. An admin gets tired of VPN issues, so they just write a firewall rule, allow SSH from anywhere.
Just let me in from anywhere, please.
Right. But you have just put out a welcome mat for every botnet on the entire planet. If you open port 22 to the world, your server will be brute forced. It's not a maybe. It will happen within minutes of you opening that port.
But admins do need to get in. If we close the front door, how do they actually manage the server?
You use a side door. It's called Identity Aware Proxy, or IAP. Instead of connecting directly to the server's IP address, you connect through Google. Google checks your identity, verified your hardware key, checks your IAM permissions, and only then tunnels your traffic to the server.
So the server doesn't even need a public IP address.
Exactly. To the outside internet, that server is invisible. It's a dark room. You can only enter if Google explicitly vouches for you.
That sounds significantly safer. Now, there is one more technical piece in the networking section that I found really interesting because it sounds completely harmless: the metadata service.
Ah, yes. The metadata service.
It sounds like a library card catalog, but the research calls it a major attack vector. What actually is it?
So every virtual machine needs to know things about itself. What is my IP address? What project am I in? What service account am I using? It gets this info by querying a local URL, 169.4.169.254.
Okay, so the server basically talks to itself to get its ID card.
Right. But here is the danger. If an attacker manages to compromise a web application running on that server, say, via a server-side request forgery vulnerability, they can force the application to query that local URL. And do you know what the metadata service hands back?
Don't tell me it hands back the keys.
It hands back the service account token, the actual credentials for the robot identity we talked about earlier.
So the hacker literally becomes the server.
They inherit every single permission that server has. If the server can write to the database, the hacker can write to the database. This is exactly why you need to disable the legacy V1 metadata endpoints, which are way too easy to query. The V2 endpoints require a specific custom header that is much harder for an attacker to forge.
And this ties back to least privilege, right? Because if the server has God mode permissions,
Then the hacker has God mode. And sadly, this brings us to another default you absolutely need to kill: the compute engine default service account.
wait, another default.
Yes. If you spin up a VM and don't specify an identity, it just uses this default account. And historically, this account has the editor role on the entire project.
An editor means
It means they can delete disks, create resources, read data, basically everything except changing permissions. It is way, way too powerful for a simple web server. You need to strip its roles entirely or create a custom identity that can only do the one specific thing it needs to do.
it really feels like default is basically synonymous with insecure here.
In the cloud, convenient usually spells insecure.
Let's pivot to the data itself. Encryption. Google encrypts data at rest by default. So why are we doing anything here? If someone physically steals the hard drive from the data center, they can't read it anyway, right?
That's true. Google managed encryption is fantastic, but it comes down to separation of trust.
Yeah.
In the default model, Google holds the data, and they hold the keys to unlock it.
So if a government agency serves Google a subpoena,
Google can decrypt it. Or if a Google employee went completely rogue, theoretically they could decrypt it. If you deal with highly sensitive data, like healthcare or finance, you want customer-managed encryption keys, or CMEK.
you hold the key.
You hold the key in Cloud KMS, you control the rotation, and crucially, you have a kill switch. If you detect a massive breach, you can just disable the key.
And the data.
It instantly becomes cryptographic noise. Even Google can't read it. It is the ultimate failsafe.
That is powerful. But we have talked about keys and secrets and passwords. One of the biggest issues in software development is where to actually put these things. We've all seen developers hard code API keys right into the source code. Here is the password to the database, just sitting in the script.
Here's a cardinal sin. You never ever store secrets in code or metadata or environment variables. You use Secret Manager. It's a secure vault. Your application asks for the secret at runtime, uses it in memory, and never writes it to disk.
We have covered a massive amount of ground here today: identity, logs, networking, encryption. But I can hear the listener thinking, I have 50 developers. I can't stand over their shoulders and make sure they don't create a public IP address. How do we actually scale this?
You can't rely on willpower. You need governance. You need organization policies.
Explain that layer.
Think of these as unbreakable guardrails on a highway. You set a policy at the very top level of your organization that says, public IP creation is denied.
So if a developer tries to do it anyway.
The API just says no. It returns an error, policy violation. They literally cannot make the mistake. You can set policies like domain-restricted sharing, which makes it technically impossible to grant access to a generic gmail.com account.
That sounds like the sanity check every security team dreams of having. But there is one more governance tool in the notes. VPC service controls. This one seemed a bit complex.
It is the heavy artillery. It protects against the authorized user, unauthorized location problem. Let's say I steal your valid MFA verified credentials. I have your key, I have your password. Usually that is game over.
Right. You are me at that point?
But with VPC service controls, you draw an invisible perimeter around your data services, like BigQuery or cloud storage. You say access to these services is only allowed from this specific corporate network.
So if you try to use my credentials from a coffee shop,
The API blocks it entirely. It says the identity is valid, but the context is wrong. It prevents data exfiltration even if the account is totally compromised.
that is a massive safety net.
It's the strongest preventative control layer you have.
I want to bring this all together now. The report lists a couple of critical scenarios. Let's walk through them to see how these layers stack up in reality. Take the mid-level admin compromise.
Okay, so picture a DevOps engineer. They get phished. The attacker has their password, layer 1. If you have FIDO2 hardware keys, the attack stops right here. The password is useless without the physical key,
But let's say they don't have the key. The attacker gets in.
layer 2. The attacker tries to grant themselves organization admin status to own the whole company. If you have restricted role-granting policies in place, they are blocked. They can't escalate privileges.
Okay, so they are stuck as a mid-level user.
Layer 3. They try to create a service account key to leave a backdoor for later. If you have an org policy disabling key creation, they are blocked again.
It's defense in depth. You are making them work for absolutely every inch.
Exactly. Now let's look at data exfiltration. An attacker hacks a web app via a code flaw. They get to the database. They run a command to export all data to an external bucket.
Just shipping the customer data right out the front door.
Layer 1. If the service account only has least privilege, it might not even have permission to export data in the first place. Layer 2. If you have VPC service controls, the network perimeter sees the data trying to leave the secure zone and just blocks the transfer. Layer 3. If you have data access logs on, your security team gets an alert that a massive read operation is happening and they can cut access.
It completely changes the narrative from we've been breached to we detected an attempted breach and neutralized it.
That is exactly the goal. Resilience, not immunity.
So we've built the fortress, we've hardened the walls. Are we done? Can we finally go home?
I really wish we could. The cloud changes every day. Developers change, new projects spin up. You need continuous assurance. You need automated tools that scan your environment every single day against these CIS benchmarks. If someone accidentally opens port 22 for testing and forgets to close it, the scanner should catch it within minutes, not months.
It's constant vigilance.
It is. But once you automate it, it becomes manageable.
As we wrap up this deep dive, I want to leave you with a final thought. We've covered a lot of technical controls today, but what is the real philosophical takeaway here?
Here is the provocative thought I want you to sit with today.
Yeah?
In almost every major cloud breach you read about in the news, the attackers didn't burn $1 million zero-day exploit. They didn't crack some impossible encryption code. They simply walked through a door that the customer left unlocked. They exploited the resources you forgot to configure.
That is a sobering reality check. But think about this too. With automated scanning tools getting faster, attackers are finding those open doors before you even realize you've created them.
Exactly. If you haven't audited your compute engine default service account or checked if your default network is still active right now, you really shouldn't assume you are safe.
Yeah.
You're likely already exposed and you just haven't looked at the logs yet.
On that note, I think everyone listening has some homework to do today. Go review your environments against these benchmarks. Don't be the low-hanging fruit for the hackers. Thanks for diving in with us.
Stay secure out there.
We will see you on the next deep dive.